So we're looking at how light interacts with matter on the nanoscale. And in this case, nanoscale for us is the nano size scale, which involves a nanometer. And for those who are not familiar, 1 nanometer is a billionth of a meter. And as a reference, it's about 100,000 times smaller than the diameter of a human hair. And so the reason we're interested in this problem is that light cannot interact with matter so efficiently because there's a characteristic length scale which is related to the wavelength of light. And usually you're interested in things that are much smaller than the wavelength of light. So you have to somehow come up with ways to improve this interaction. And nanotechnology enables this in some unique ways. So let's briefly go over what light is. So light is an electromagnetic wave. And for electromagnetic waves, what we have is electric and magnetic fields oscillating in time and space in a unique wave. And this wave, actually, it's a wave it propagates. And the wavelength, which is our characteristic length scale, is determined by the speed of light divided by the number of cycles this wave is oscillating, which is also known as the frequency. And another way to look at wavelength, it's essentially how much the wave propagates in one cycle of the oscillation of the wave. And we use electromagnetic waves for many things in our lives. So basically, the wavelength determines actually what kind of waves we deal with. In my particular case, I'm going to look at the case of light, but we use it everywhere. Radio waves are also electromagnetic waves. So here what you see is the transparency of the atmosphere. And you see some openings in this transparency window. So one window is here in the radio waves, or microwaves, if you like. And this is, so since the atmosphere is transparent, we use this for radio communications with satellites, for example. And we have another window, transparency window, that's also of interest to us. This happens to be in the infrared portion of the spectrum. And this is, for example, what we use for imaging from satellites when even in dark, because we can see, even there's no sunlight, we can still see objects with infrared, through infrared emission of light. And probably the most important or interesting portion of the spectrum, or maybe even fundamental for us, is this region which we call the visible spectrum. And this is where the light actually, so basically light as an electromagnetic wave exists in this portion of the electromagnetic spectrum. And as you see, this is the transparency of the atmosphere. It happens to have a transparency window, which is good because we can have life now on Earth, because most of the sun's radiation happens to be also in this visible portion of the spectrum. And just the lengths to give you some sense of length scales that we deal with. So you can have, again, electromagnetic waves of any wavelength. For example, you can have radio waves. If you have a radio wave, you're talking about a wavelength which can be on the size of buildings or even kilometers. And then from there on, you can go all the way to the other extreme, which is the gamma rays. So when you deal with gamma rays, they're electromagnetic waves, but their wavelengths are very, very short. It's on the size of a nuclei of an atom. And similarly, X-ray, you see it's slightly longer wavelength. But again, we're interested in this visible portion here, which many interesting things also happen. And for some sort of a length scale, so when we deal with visible light, the wavelength we have is about a millionth of a meter or a micron, and that happens to be on the size of a bacterium. So this will be about a micron. And so some of the things that I will talk about will be light in this portion of the spectrum. Okay, so let's talk about optical properties of things in bulk or on the macro scale. So for this particular case, let's look at the optical properties of metals. Okay, the optical properties of metals are rather boring. So if you just shine light on a piece of metal, well, it's just a boring mirror reflector. Well, after all, maybe it's not so boring for some of us, but in general, it's boring. Now let's see what happens. Instead of dealing with macro scale materials, we go to the nanoscale. Now, this is an example of ancient nanotechnology, and I'm going to explain to you why this is ancient nanotechnology. This is of the famous Lycurgus cup, which is displayed currently at the British Museum in London. And this was made around the 4th century AD by these ancient glassmakers. So the interesting thing about this is, if you were to look at this from outside by illuminating from the outside, looking at it in reflection, it appears green. But if you were to look at this in transmission, this appears red. Okay? And similar thing also happens with these stained glass windows of the 12th century medieval cathedrals. And all these colors actually come from the fact that these ancient glass makers figured out a way to use nanotechnology back then. So here's their secret. So if you were to take a piece of this glass, you would end up seeing these small nanoparticles. In this case, it's a nanosphere made of gold, which is embedded in glass. Okay? So, of course, this was done through trial and error for their case. What they were doing was they would take molten glass and throw in shavings of gold, and if they can optimize the conditions, they can end up getting these particles embedded of the glass. And you see the striking red and green contrast in the case of the Ertugrul cup because these gold particles happen to have a resonance around green portion of the electromagnetic spectrum. So they would, because of this resonance, they're going to strongly scatter or reflect the green portion, but not other wavelengths. So that's why you would see it as green in reflection, and it's going to appear as red because it's going, in the case of transmission, it's going to absorb some of the light. Now, with the advances in nanotechnology, actually, we can do better than these medieval glass makers. So we can use nanotechnology to make these nanoparticles of metal in any shapes and sizes, and using that we can actually engineer where we see these interesting effects in terms of the spectrum, in terms of color, for example. And you can see the length scales here. These are all about less than 100 nanometers. And so what's this good for? Now, one example is when you manipulate electromagnetic waves in the radio wave frequencies, we typically use antennas. We have one of those in not something as big as this. This is from the 80s when you used for ultra-high-frequency TV communications, but currently we have much smaller antennas in our cell phones. But we are lacking the concept of antenna in the optics domain or for visible light. So now, using nanotechnology, we can come up with a scheme to introduce the concept of the antenna in the optical domain. Now here you see this is called a Yagi-Uda antenna for radio communications. And this one is its optical analog for visible light. So here you can see the length scale. Here you see the scale bar, which is 200 nanometers. This whole thing fits on a micron footprint. So just to give you an idea, this is, again, it's 100 times smaller than the size of the human hair, the diameter of the human hair. Or again, it's maybe, for those who are familiar, this is on the size of a single E. coli bacterium. Now, what can you do with this? So conventionally, when we deal with light, we use not antennas, but we use lenses to manipulate the propagation of visible light. And so one prime example is probably optical microscopy. In optical microscopy, what we use is these objectives, and these objectives are complex lenses. What they do is they just focus down light. But this has a fundamental physical limitation in terms of how small you can focus the light beam. And this would be on the order of the wavelength, because that's the characteristic length scale, if you will. But most of the time, the things that we're trying to see or interact with are much smaller than this. For example, take a protein. The size of a protein is 3 nanometers, and the spot for red light would be on the order of a micron. So this is comparing my thumb with the volume of this entire room. So it's like looking for a needle in a haystack. So now, what can we do with these antennas? So one idea is, for example, we can use these antennas in conjunction with the optical techniques we currently have. So basically, we put this metal piece, which acts like an antenna for light, in the focal point of this objective. And what you see is now, instead of getting this, this optical spot, which is limited by the wavelength, now we can localize this further down using this antenna, which acts like a resonant structure at optical frequencies, and we can get easily tens of nanometers. So what can this be good for? For example, if you're trying to use this for biomarker detection in the optical domain, we can use this for trying to detect very small concentrations of molecules, because they're going to, so this allows us to optically interact much more effectively with these molecules. And then similarly, one application would be in the realm of night vision cameras. So here you see how a night vision camera works. This is the visible image, and this is a night vision camera. Night vision cameras usually look at the radiation from your body at your body temperature. As you can see things that are not visible to the visible light. And we can use these antennas for making these absorbers, which are used in these specialized infrared detectors or cameras, if you like. Thank you so much for listening.